Hello, everyone. I'm Xing He, FAE of Automotive KA Center from NOVOSENSE Microelectronics. Today, I'll introduce stepper motor stall detection. There are mainly 4 parts. Part 1. Why is motor stall detection necessary? Part 2. Principle of stall detection by NOVOSENSE's stepper motor driver chips. Part 3. Demonstration of stall detection process using NSD8381. Part 4. Overview of NSD8381 and NSD8389. Motor driver chips. Part 1. Why is motor stall detection necessary? Stall detection ensures safe, reliable motor control, preventing damage, improving stability, and meeting safety standards. Key purposes include: Part 1. Prevent motor damage. Part 2. Protect drivers from high current. Part 3. Improve system reliability. Part 4. Meet safety standards. Part 5. Performance evaluation. Part 6. Diagnosis and improvement. Part 2. Principle of motor stall detection. NOVOSENSE's stepper motor driver chips use the back electromotive force method for stall detection. Formula 1 calculates the motor winding voltage. It shows that during motor rotation, the winding voltage includes back electromotive force voltage. When the motor current is 0, the winding voltage equals the BEMF. Formula 2 calculates the BEMF in the motor winding. It shows that when the motor stalls, the angular velocity and BEMF are 0. Thus, BEMF changes can indicate a stalled motor when the current is 0. Now, let's focus on the demonstration of stepper motor stall detection process. Step 1. Prepare the relevant tools and configurations to make the motor rotate normally. Hardware configuration includes NSD8381 demo board or customer's PCB, stepper motor, serial port tool or MCU control, 12V DC power supply, signal generator, oscilloscope, serial port transmitter host interface or customer's own MCU control interface. The software configuration enables the stepper motor to rotate in 1/8 microsteps. Demonstration of motor rotation. Part 1. Connect the host computer and serial port. Part 2. Power the demo board. Part 3. Provide pulse signal. Part 4. Send register configuration commands. Finally, the motor rotates. Step 2. Use an oscilloscope to measure the waveform of out A1, out A2, or out B1, out B2 to ground after the motor starts rotating, effectively measuring the motor winding voltage. In the waveform, the section without PWM modulation indicates 0 driving current, where the yellow arrow marks the BEMF voltage. The duration of the yellow dotted line represents the CV delay needed for stable BEMF measurement. In the example, the measured BEMF is 2 volts. And CV delay is 350 microseconds. Step 3. Configure the config5 register. You need to configure CV delay, enable CVEN, and configure CV stall. CV delay is the coil BEMF voltage conversion delay configuration. A configurable value from 1 to 31 corresponds to a delay in the number of PWM cycles, starting from 0. After which the coil BEMF voltage conversion begins. CV delay tested in Step 2 is the reference value for this configuration. If the value is 0, voltage sampling is performed at the end of 0 current. It is suitable for motors with relatively fast rotation speed. CV stall is the configuration bit for the number of conversion when the coil BEMF voltage is stalled. The number of consecutive conversion of the coil BEMF voltage during stall detection can be configured with the minimum value of 1. Step 3. Configure the config5 register to 8000 and sample the coil voltage at the end of 0 current. Step 4. After the config5 register is configured, the motor is still rotating normally, At this time, read back CVA, CVB, CVC, and CVD through the serial port. Record the CV value at this time and compare it with the BEMF value measured by the oscilloscope. This step requires config 5 to be configured so that the readback CV value is as close as possible to the BEMF value measured by the oscilloscope. If there is a deviation between the readback value and the measured value, CV delay and CV stall of config 5 need to be adjusted. As demonstrated, the CVA, CVB, CVC, CVD registers return a value of 008E maximum, which is converted to a high value of 1.94 volts, close to the measured BEMF of 2 volts. Step 5. Make the motor stall and measure the waveform of out A1 to ground and out A2 to ground again. In the same way as in Step 2. As shown in the waveform, the BEMF voltage shows 0 volts. Step 6. At this time, the motor is still in a stalled state. As demonstrated, read CVA, CVB, CVC, and CVD again. The readback values in the stalled state are 001B maximum and 0000 minimum, which are converted to the low values of 0.35 maximum and 0 volts minimum, basically consistent with the values measured by the oscilloscope. Step 7. Configured CVLLA and CVLLB. CVLLA needs to be larger than back electromotive force method, but smaller than CVLLB. From Step 3, we get value of 1.94 volts. From Step 6, we get the low value of 0 volts. Thus, CVLLA is set to 0.52 volts, CVLLB to 0 volts, and CVUL to the default value, 28 volts. Step 8. Let the motor run and then stall and read back the STA1 register at both time. As demonstrated, set the config 5 register, configure CVLLA. When the motor rotates normally, read back the 01 register and CVA, CVB, CVC, and CVD. At this time, the CV return value is around 008E. The status register has no fault report. Then, stall the motor and read back the status register. At this time, 05 is read from STA1 register, and a stall fault is reported. Read back CVA, CVB, CVC, and CVD at the same time. The returned BEMF is 0. This means that the stall detection is successful. Finally, let me introduce 2-stepper motor driver chips from NOVOSENSE. NSD8381 is a highly integrated dual-phase bipolar stepper motor driver for automotive applications, ideal for controlling automotive headlights, electronic expansion values, and HUD position assessment. NSD8381 supports up to 1.35 amperes full-scale current, 16-level current regulation, up to 32 microsteps, and multiple decay modes. It allows 4 independent half-bridge operations and includes protection as well as open-load diagnostics. Additionally, it integrates the stall detection function for fault output and stall diagnosis. NSD8389 is the latest automotive dual-phase bipolar stepper motor driver released by NOVOSENSE. It supports up to 1.5 amperes of stepper motor currents, 256 microsteps for motor control, and 8 decay modes. It integrates multiple protection functions such as bus undervoltage protection, overcurrent protection, over-temperature protection, open-load diagnosis, and overcurrent protection. It also supports stall detection function, suitable for applications with higher precision requirements for stepper motors. If you are interested in NOVOSENSE stepper motor driver chips, please consult NOVOSENSE's official website. Thank you for watching.